Good morning, everybody. I've got a tiny bit of the flu, so I got a lot of tea and the microphone. Is the volume okay for everybody? Up, down? Bit of up? It's good? It's good? All right. So, as Yale said, I'm an analyst, which is different from psychoanalysis. But since I'm Austrian, as Sigmund Freud, if you've got any questions about psychoanalysis, feel free to come up afterwards. In the meantime, I'll tell you about one of my favorite stories in math. And it's also one of the oldest stories in all of history. It's 3,000 years old. And it's actually so old we're not quite sure when it happened. But I like to think it did. What you see in the picture here is Dido, who was a queen in what's now called Lebanon. That's over here. And she ran into some sort of political difficulties, right? That happens. So she took her people and she fled all the way to what's now Tunisia, and back then had an entirely different name, and tried to get a fresh start, right? And we know about this story from Virgil, and he's not the most trustworthy narrator, so as I said, we're not quite sure when it happened. But he tells the story as follows. He says, Dido with her people arrived in Tunisia, and spoke with the local king and said, you've got a lot of space here. There's a lot of empty space. I need a fresh start. I've got a couple of people. I wouldn't need too much. Could you give me some of your land? Right? And the king was not a nice man. The king said, well, yes, of course, I will give you land. As much land as you can cover with this T-shirt. And he gave her, well, he didn't say T-shirt. He said ox hide, because it's 3,000 years ago. But he essentially gave her a T-shirt and said, you can put it wherever, and that is going to be yours. Right? So he was not a nice man. But she was very smart, and she was one of the first mathematicians. And what she did, you can see here, she told her people to cut the T-shirt up into a really long loop. So she said, okay, whatever's covered by the T-shirt is mine. So she took the T-shirt and cut it into a long, loopy string. Okay? And then once she had that loopy string, the problem is how do you arrange the string on the ground? So here you see three possible diagrams. The black lines are always the long, loopy, cut-up T-shirt. And then it's on the ground. And there are many different ways you can arrange it on the ground, right? There's many possible shapes you could choose. And the question is, which one do you choose? And she said, we'll go for the circle, because the circle has the largest area. And that makes her the first mathematician, or one of the first mathematicians, and she's absolutely right. So among all sets in the plane that have a certain fixed perimeter, a fixed boundary, a boundary with a certain fixed length that you cannot change, right? You cut up the T-shirt, and that gives you a loopy string of a certain length, and you cannot change the length anymore. You've cut up the T-shirt. You've got the thing there. The only thing that can change it is the area inside. And the way to make the area maximal is to arrange it in the form of a circle, right? So this is a pretty nice statement. It's also a very old statement. And you can see it another way. So there's always two ways to think about things. And here the second one is you fix the area and look at the boundary and say among all sets in the plane with a fixed area, everything has, you can put, a square with area 1. You can put a circle of area 1. You can put a hexagon. It's a regular polygon with 6 sides. That's the one in the middle. You can put that down. All of them are going to have a certain fixed area, and then the boundary length is going to be the smallest for the circle. Right? So this is it. And it seems like a beautiful statement, and it seems like the story should be over now. Well, it's not. First of all, this fundamental fact has been known by nature for a very long time. I'm talking millennia. What you see here is the fat that's swimming on top of the soup. I don't know if you've ever taken a closer look, but it's a bunch of tiny circles. It's a bunch of tiny, it's also the tastiest part, I think, but it's a bunch of tiny circles, and it's a bunch of tiny circles for the very same reason. And nature goes even further than that. So if you have a look at this beautiful animal, I mean, if you have a cat at home, that's how cat sleeps. I think some dogs as well. Any idea why? Yes?
So they have more space to sleep and no one can disturb them?
Oh yeah, no, no one's disturbing this one, right? It's so cute. And if you look on top, right, it's a perfect circle, right?
I think it's that they have the least surface area to lose heat from.
Bingo. Bingo. Also not being disturbed. That's important, right? You like your sleep. No, this way, the animal has the least surface area, so it's not exposed to the cold weather as much. And animals have known this all along, and it's sleeping in a perfect circle. And you know this too, right? You know how I'm lying on the beach? On the beach, I'm like this. And when it's winter and I walk to the office, I'm walking like that. Because I'm decreasing surface area. I don't want to be exposed to the wind. This is how you do it. And of course, the cats know the alternative around. So this is the family cat in summer. You want to increase your surface area. You want to be as far away from a circle as possible. All right, so here's a political question. I don't know whether there's any princess or princesses here, but where would you like to be king or queen? Well, these are two possible kingdoms to choose from, and let's say they're both equally nice. Say the same amount of nice rivers and beautiful mountains, maybe a couple of lakes. The only thing that's different is the shape. They're also equally big, same amount of gold, right? So which one would you choose? Mm-hmm. For the enemy to get there, yes. Congratulations. The young man is perfectly right. Right? So here's my troops. I've got 4 soldiers, right? I'm a small king. I'm happy to have 4 soldiers at all. And they're patrolling my boundary. Then if there is this sort of invasion happening, I like to be in the circle, because in the circle I can reroute the troops. Whereas in the long, thin strip, I'll never see them coming. Now, maybe I'm simplifying things a bit, and probably I am. And maybe I'm not. So here's a map of Paris, 1615. You see the city wall, perfect circle. Let's go further. This is a map of Europe. And I would have taken a map of the US, but the US is not representative because the US doesn't invade itself a lot. But Europe invades itself a lot. So here's a couple of shapes in Europe, the common states. Let's look at the circles in there. There are many. And again, now here I should say, maybe I'm oversimplifying this a bit. It's not just a matter of geometry, because you've got mountains that increase separation. You have sociological facts, such as people like to be ruled by a king who speaks the same language. Right? There are many reasons. Some countries like this, some countries like that. So I'm simplifying when I say it's the shape, but the shape does contribute, and you can see it contributing. So one interesting fact is that Italy, right? Italy is not a circle at all. It's a boot-shaped form. But if you look at the part of Italy that's bounding with the rest of Europe, that part here is where you actually meet your neighbors. It's a perfect circle. Same. Right, getting an actual circle is very difficult, because in the end people say, let's take this river, let's take that mountain. Those are nice borders.
Italy is long.
Right, Italy is very long.
So you can't have that as a circle.
Very true. That's just a boundary. And the same goes for France. France is, if you look at the part that's bordering with the rest of Europe, is approximately a circle. Again, I don't want to oversimplify geopolitical facts, but it is a first approximation. And here's something I found while looking this up on the web. So this is a discovery made a year ago. Apparently, if you put something that's vaguely circular shaped on the ground, and here it's a cell phone charger, then cats like that. And they will sit inside. So someone discovered this, I guess, by chance. You drop the cell phone cable and suddenly the cat is sitting inside, right? And you repeat the experiment and the cat is still sitting inside. So someone put this up on the web, and then of course people started experimenting with their own cats, and it seems to work very well. And it's not quite clear why, because a cell phone cable doesn't offer you increased protection. That was the first theory, increased protection. The cups are not protecting you from the dog. But maybe cats like nicely shaped territories. And I've seen this experiment repeated with bananas. We put 3 bananas, the cat will still sit inside. And it even works for a couple of other animals, but not as well. So it seems like cats is really the one. Cats like circular shapes. And if you've got cats at home, I'm sure some of you do, Give it a try. Okay, here's something completely different. And again, you will see the circle as a dominating shape. This is serious science. It's so serious that it has a complicated name. It's called the internal diffusion limited aggregation model. But what it really is a game. You know, you can't say, oh, I'm going to work and play games. You're like, I'm doing serious science. So here's serious science for you. You start in the center, and that's the rule. Rule number 1, you start in the red square. And then you go into a random direction. You go up or down or left or right, completely randomly. And whenever you hit a square that you've not seen before, you color it green and go back to the original red point. And play the game again. So we'll take a random step. I don't know where it's going. It's going right. OK, now we go back to the red square. Another random step. OK, we go up. Back to the red square, another random step. This time it's left. Go back to the red square. We take a random step, starting from the red square. OK, we've gone up, but we've gone up before, right? So it doesn't count. We play the game until we hit an empty square. So what do we do now? We go left. OK, well, I mean, it's random, right? You throw a coin or a dice. We go back to the red square. Now it's down, back to the red square. We go down again, but we've been down before, so we keep playing the game again and again. We go back up again. OK, that can happen. We keep playing. Left, and now here. OK? So this is the game, and it models cellular growth and these sort of things, or the growth of crystals. It's a growth model that's studied by physicists. It's also a fun game. What happens if you play this game for a really long time? Well, number 1, you'll get bored. But number 2, you can use computers to actually do it. And this is what you get after 1,000,000 steps. And the funny thing about this is, I mean, it's clearly a circle, and it makes sense that it's a circle, right? Because if you've got something that's close to your center, but you've not been there before, you're sort of likely to go in there, right? If I were to draw it, whenever you've got a shape like this, right, and you start here, you're pretty likely to go in here, and then back to the square, and here, and back to the square, and here, and back to the square, and then you will turn it into a circle. And if you zoom in on the boundary, it's actually quite interesting. It is not straight. It can't be straight. It's squares. And it gives you sort of a weird landscape that's pretty rough. And that is still not properly understood. So understanding that landscape is an open problem. Very pretty one. OK, back to math. So Dider's statement says, among all sets in the plane with a fixed area, the circle has the smallest boundary, or conversely, if you've got a fixed perimeter length, the circle has the largest area. And the good thing about math is you can always ask why, right? So the teacher tells you it is so, and you can say, why? Why? You can always keep going. There has to be an answer. And I've not given you any sort of answer. I've told you that it is the case and that it appears in nature a lot. But that might mean very little. So what's the actual reason? And someone might say, you know, you've given us all these nice examples from nature. So certainly nature knows best, right? Nature has been implicitly thinking about this for a long time. This is an example of an ice that is hexagonal. So it's a regular polygon with 6 sides. If you go online, you'll see there's actually a lot of different types of ice, and one of them has a hexagonal shape. Here's another and more striking example. So my favorite planet, Saturn, and you'll say, oh, it's perfectly round, right? It's another circle. Yeah, it is, until you zoom in on the North Pole. So here's a picture from the North Pole of Saturn. You see a hexagon. There's a hexagon on Saturn, and no one knows why. Okay, it was discovered rather recently. No one has any idea why there should be a hexagon on Saturn. There seems to be some sort of storm that's raging on, and it's twice the diameter of Earth. It's huge. And it seems to be like a sort of a tornado that stays there for hundreds of years. But why is it hexagonal shaped? Why is it not a circle? Well, you see, there are things in nature that are not a circle. So just saying that it happens like that is not, it's not sufficient reason to say it's got to be the circle.
Maybe it's because there's like 6 different directions.
But why would there be 6 different directions of wind? Why not 7 or 5? Actually, here we don't know. But for the circle, we do know. That's a good part of the story. So as I said, the story started 2,800 years ago, and it took 2,700 years to complete. It's a really long story. And the first result is by Zenodorus, about whom we know very, very little, but who said the following. He says, if you've got a triangle with certain lengths, and you build a triangle that uses up the same amount of boundary area. So in the story of Queen Dido, you cut up your T-shirt into something that's this long, and you can build two triangles out of this. You can build this triangle, maybe not quite, and you can build this triangle, and they use the same T-shirt. And Zenodorus says that the second one has a larger area. Okay, so that's one of the first steps. It says that being more regular increases your area, which makes you a better candidate. And he showed the same statement for polygons with 4 sides and 5 sides. Yet again, this means very little, right? The life is not made up of triangles. If it was just triangles, we would be done by now. But we're not, because there are many, many complicated shapes. But this was the first step. And he's remembered for that. After 2,000 years, we know nothing else about him. We know he did that. And then for 2,000 years, there was nothing. There was absolutely nothing. People didn't know what to do. They had no ideas. It's a very tough problem. And then the main hero of the story is Jakob Steiner, who was a Swiss mathematician around 200 years ago. And from what the sources tell us, the right picture is more accurate. He was a pretty angry man. So he would vaguely argue for something. It's got to be like this. It's got to be like that. And then if you say, but why? He would get very angry and scream at you, but okay. But he had one absolutely brilliant idea, which is called the Steiner symmetrization, and it's so brilliant and used so much that people actually drop the name and say symmetrization, because it's clear that he did it. And I want to illustrate it with a slice of pizza. So what Steiner did is he was just playing around with geometry, okay? He was just having fun with shapes, and he discovered something absolutely amazing. He discovered a game that takes a shape and makes it more regular. It's called the Steiner symmetrization game, if you wish. And it's played in a very easy way. You take a shape, you take a line, and then you take the lines that form a 90-degree angle. Let's say this. And then you cut it along those lines. So you cut the pizza in slices and move the individual slices up and down to make them as symmetric as possible with respect to the black line. You move this one up, you move this one up, this one up, this one up. This stays a bit, it goes down, down. So okay, I have now a new weird pizza shape, which clearly has the same area, right? I mean, you cut up pizza and move it around, the area of the pizza doesn't change, luckily for us. And you can do it with more complicated shapes as well. So the game here is, you start with the shape on top, you cut it along those lines, and then you move those lines to be as symmetric around a big line as possible. I'll do one more example here. So I'll take the letter A, because why not? You start with any shape, so this is the shape. And you take one big line. It doesn't matter which one it is. You can take any big line you like. Okay, and then once you have that line, you cut it up. And then you move those shapes up and down to make it as symmetric as possible. So the new picture would probably look a bit like, this one I got to move down a bit. So it looks like this. This one I'm moving down a lot. So it looks like this maybe. This one is pretty fine the way it is. This I got to shrink a little, left and right. This just moves here, and these as well. So you get this new shape, and if you do it correctly with enough lines, this new shape will be perfectly symmetric around the big line, and clearly will have the same area. Now, how does this concern us? It concerns us because it keeps the area the same. But if you play this game, the perimeter becomes smaller. The boundary shrinks, which is great, right? You've got a game. You start with a certain shape. You get a new shape that has the same area, but a smaller boundary. And you keep playing again, and you get another shape and it has a smaller boundary still, and another smaller boundary, and another smaller boundary. So if we just keep playing this game, what happens? We get a circle. Right? So I mean, here this is not yet a circle, right? But maybe now I'll play the game again with this line, and with that line, and another couple of lines, and it will start to look more and more like a circle. And once you've reached the circle, the game is over. It's actually, you can still play the game, but nothing is going to happen, right? Because you take any line, and if you cut it up and move it up and down, you'll get a circle back, because a circle is symmetric with respect to any line. The game is over. All right, so symmetrize with respect to that line, and you get the circle back. So the game keeps on going until you hit the circle, and then it stops. That sounds pretty good, right? We're trying to find a shape with a certain area that has the smallest perimeter, and we get a game that makes it smaller and smaller and smaller and smaller. And when it hits the circle, it stops. Right? So this is what Steiner said. He said, I found a game that keeps the area the same. It doesn't change the area at all. But the perimeter becomes smaller and smaller, or maybe stays the same, but it doesn't grow anymore. And you can always play this game until you hit the circle. When you've got a circle, the game stops. And therefore, the circle is the one shape that has the smallest possible boundary, because I can't play the game anymore. Now, is this a good reason? Yes, no. I think it's an amazing reason. I think it's a beautiful argument. But there is a tiny, tiny gap. And what I'll tell you now is something it's not complicated, but it took the best mathematicians of the time another 50 to 70 years to realize. It's a great reason. But it has a tiny flaw. And the tiny flaw is we don't know whether there is a solution. I'll talk about this at great length, no worries. So Steiner himself was completely convinced. He said, this solves the problem. It's 2,700 years old, and I've solved it. He was very proud, and he was very angry when you doubted the completeness of the solution. And then Oscar Perron came up, and he came up with a great example. So what Perron did is he invented a game of his own and said, I can do the same type of argument you do, and I end up with complete nonsense. So we got to be careful. So his game was the following. He says, take any number, like 3, and multiply it with itself. OK, that gives me 9. OK, multiply that with itself. That gives you 81. OK, you multiply that with itself. It gives you a large number. All right? Or you do 2, and you get 4, and you get 16, you get 256, and so on. It's a very simple game. And Perron, who was a much nicer man, one should say, he was very nice. You can see it, he's very nice. He said the following. He said, this is a game that takes any number and gives me a bigger number. There is one number for which this doesn't work. What's the number? What's the number where nothing happens? 1, precisely, it's 1. Nothing happens with the 1. And Perron said, I've got a game. It always gives me a bigger number. And if I look at the biggest number, the game has to give me the same thing again, like the circle in Steiner's game. The biggest number is the one that doesn't change. Therefore, 1 is the biggest number, because it's the only one that doesn't change. Now, that's nonsense, right? We know 1 is not the biggest number. But in terms of the argument, it seems to be. And if we compare the two arguments side by side, we see they line up perfectly. So Steiner said the circle is the shape with the smallest perimeter because he has a game. And for everything that is not the circle, you get a new shape that is better. The circle is the only shape for which you get something that is not better. Therefore, the circle has to be the best shape. And Perron says, well, 1 is the largest integer because I've got a game that takes any integer and gives me a bigger integer back. And the only thing for which this doesn't work has automatically to be the largest integer. And therefore, 1 is the largest integer. It's quite puzzling, isn't it? And actually, both are right. So Perron is right in saying that if there was a largest number, this argument would show that 1 is the largest number. And then everything would break down. Okay? He's sort of intrinsically right, assuming there is a largest number, but there is no largest number. And the same way, Steiner is perfectly correct in saying the circle has to be the best shape if there is a best shape. There might not be. And this is subtle. Again, mathematicians get very passionate about these sort of things, so there were fights. People got actively angry at each other for believing it or not believing it, and it's a passionate science. So what goes wrong in the second game? What's happening in the Perron game is the numbers get bigger and bigger and bigger, and they get more and more different from each other. Whereas in the Steiner game, the shapes get more and more similar to each other. And eventually, this has to be the reason why it works. Right now, it's not clear. And this is the final mathematician who appears in the story. And he solved the problem by, again, devising a beautiful game. And if you've stopped listening to me, which is maybe not a bad idea, you can start again, because this is something completely new and unrelated. It's an entire game in itself, and it clears up all the mystery. So this is Blaschke, and Blaschke was the first person to systematically study convex shapes. And convex is a very fancy word. It's even Greek, or maybe Latin. Well, it's very fancy in any case. And it's just a shape with the property that from every point you can see every other point. Right? Every point you pick, you find another point that works perfectly well. And here's an example of a shape that is not convex. So the second shape is not convex because you can't see from x to y. There's sort of a wall in between. This room is perfectly convex because I can see everywhere, because you all need to see the blackboard, otherwise it defeats the purpose. Well, I can't see under the seat, so you might argue maybe not. Let's take a look at a couple of letters. So here's the letter D. It's perfectly convex, right? You can see everything from everywhere else. Here's another nice letter. It's a P. P is not convex. Right? You can't see from here to there. There's a wall in the middle. Yes?
D isn't either, because D
I didn't draw it very well. That's true.
small part that towards the
Oh, you're saying your D looks like this. Then it isn't either. That is perfectly true. My handwriting is very bad, so my D's look perfectly convex. Nice handwriting, the D is not convex anymore. O, that works in any handwriting. Okay? Okay, and here Blaschke came up with the following amusing insight. If you start drawing a lot of convex shapes with area 1, and you try to draw as many different convex shapes as possible, it's not so easy. Right? You can do a triangle, and you can do a square, maybe a circle. But after a while, you'll run out of options. And the shape below, right, that's not convex. And if I'm allowed shapes like this, I can draw many, many different shapes. Right? Right? Then most numbers are not convex, right? So I can write down 1. That is a perfect nice shape. I can write down 2. That's another nice shape. And I keep going. And I'll be fine. Even after like 1,381,000, I get a perfect shape, and they're all very easily distinguishable because I can read numbers. But if I restrict myself to purely convex shapes, it's not so easy because there are not that many different convex shapes. And he had the following idea. He said, assume I were to cover the entire blackboard with convex shapes. So I erase everything I've done, and I draw a lot of convex shapes. Then you'll be able to find some that look very, very similar. By which I mean, if you squint your eyes a little bit, you'll be fine. You'll not see the small differences. And if you keep drawing and fill up more and more and more and more blackboards, you'll actually be able to find two that become more and more indistinguishable, become better and better. So here's an example. Here's Gauss's favorite form. Gauss was a very famous mathematician, and he liked this shape very much. And he actually said that when he died, he wanted to have this shape on his tombstone because he was closely identified with it. And the stonemason said, well, this is not going to be possible because the shape is virtually indistinguishable from a circle. It really looks like a circle, right? So this is one example of this statement. If I were to say I start with a triangle, that's perfectly convex, right? I take a square. So 3 sides, 4 sides, 5 sides, 6 sides. And you keep going. You have infinitely many shapes. All of them are convex, and all of them are different because you can actually count them, right? Okay, this one has 28 shapes, so it's different from the one with 29 shapes. That's true. But if you don't look too carefully here, it really does look like a circle, doesn't it? And it gets even better. And this is now maybe a bit philosophical, but this is the reason why Steiner's process is working and Perron's process is not working. So I want you to picture the following game. And that's a very nice game. So this is a mountain range. Okay, we start here. Maybe this is our initial shape. Okay, this is the area, if you wish. But the philosophical implications are the following. If you start on top of a mountain and you want to go down in the valley, and you've got a process that makes you go down, such as Steiner's game, right? You decrease the perimeter while keeping the area the same. If you always go down, the thing you need to make sure is that there's not an infinite hole. All right? If there's an infinite hole, you're in serious trouble because you can always go down and go down and go down, and you'll never reach the bottom. And this is what corresponds to the biggest integer that doesn't exist. And this corresponds to the shape that doesn't exist if the circle is not the optimal solution. You fall into a hole. So if you actually go down the mountain, how do you make sure that you're in that situation? And Blaschke's argument was very simple. It's like if you keep walking down, and there's the same kind of cherry tree that you see all the time, you got to be in this scenario. And the cherry tree has to be in the center. Because otherwise you wouldn't see it that much. If the cherry tree was here, you would pass it once and keep going down. And if there was an infinite hole, you would see the cherry tree once, and then you would keep going down the hole and not see it again. But if you keep seeing the same cherry tree over and over and over again as you keep walking down the mountain towards the lowest point, then the cherry tree has to be in the lowest point, right? It's like if you go to Florida to go to Disneyland and you keep seeing Mickey Mouse, you're probably in Disneyland and not lost in Texas, right? That's the principle. But if you don't like this sort of reasoning, you can just focus on the game itself. The game itself is, given infinitely many convex shapes, find two that are very, very similar. Well, yeah, so I give you a couple of things like this. They're dancing around, and I give you infinitely many. You just have to find two that are very, very similar. That sounds really complicated, okay? It's something that you might not want to do. It sounds boring and cumbersome and exhausting. But there is a nice little trick. And the trick is called the pigeonhole principle, and I did not come up with that name. But it says if you put 5 pigeons into 4 holes, there's got to be one hole that contains 2 pigeons. All right? And this you can apply in many, many settings. So suppose you've got 13 people in this room, which there's certainly 13 people in this room, then there have to be 2 who are born in the same month. Otherwise, you run out of months, right? You can't have 13 people be born in all different months. Yes?
Just like, with the exception of a leap year.
Even in a leap year, you still have 12 months. I'm not counting days.
366 people.
I'm not counting days, I'm counting months.
I know, but it's the same thing.
I wish.
You have 365 days.
If it were days, yes. If you need 367 people to have them all be born on different days. To have 2 be born on the same day. That's true. So here's an infinite version. Suppose you have all the integers and you want to color them with numbers. And you have 3 different numbers, red, green, and blue. Then at least one color appears infinitely many times. Otherwise, you run out of colors, right? So if everyone appears at most 300 times, after 900 numbers, you're out of colors. And if every color appears at most 2,000 times, you run out of color after 6,000 numbers. And if everyone appears only 1,000,000 times, after 3 million numbers, you're out of color. So one of the colors has to appear infinitely many times. And this is what we'll now do. We'll take the shapes, infinitely many convex shapes, and we'll devise a way to put them into different holes. And then we'll say one of the holes has to have infinitely many shapes, so they gotta be very similar. And then we look at that infinite subset and keep refining. Let me just show you an example. So I've had a couple of cats already, so I'll keep going. I'll use this cat to watch out whether the region of space it is in is occupied by the shape or not. So whenever there's nothing going on, the cat is like a small guard that's paying attention. And if there is a shape, it will get very excited and say, the shape is here. So I'll use 16 cats initially. And if there's a shape, the cats are trained to go, wow, right? And this is my way of detecting shapes. Another shape, and the 2 cats are trained to meow. Another shape, meow. Now, think about it. I've got infinitely many shapes. One shape after another, after another. But I only have finitely many cats, and I have a finite number of ways the 2 cats can react. Right? They can meow or not meow, and I only have 16 cats. So it's the same as the numbers and the color. After a while, I'll be running out of reactions. So one of the cat reactions has to appear infinitely many times. So for infinitely many of the shapes, the cats have to be react in a certain fixed way. Suppose it's that one. Now that tells me a lot. I found an infinite number of shapes where the cats react like this. What does that tell me about the shape? Well, not so much, but not nothing, right? So this is one possible shape that works. This is another shape that works. This also works. They're still sort of similar, different, but they get more and more similar. So it tells me a couple of things about where the shapes could be, but it also tells me about points that cannot be in the set. So if I have a set that makes the cats react like this, it is not possible for this point to be in there. And the reason is because they're convex. So I can see every other point from where I am. Meaning in particular, the 2 cats, they can see each other, right? This point here is in the set. This point is in the set. So they can see each other. So the blue line has to be in the set. And if this were now let's assume for a little bit that this were to actually be in the set. And these 2 lines would also have to be in the set because you can see from every point to every other point. And then that cat would actually have to react as well. But it doesn't. And therefore, this point is not in the set. And if you look carefully, you see this entire region here cannot be in the set because it would make that cat meow, and it doesn't. All right, it seems still like very little information, but if you use a lot of cats, we can use a lot of cats, right? So here I've got, I don't know, maybe 100 cats, and I still know one of the cat configurations has to appear infinitely many times. It might be this one. Then this now tells me this is a pretty good information already because it tells me the shape has to be between those 2 boundaries. So every cat has to be in there, so all the connections between the cats are also in there. And if I've got a point here, then those cats here would have to meow, but they don't, so this point is not allowed in here. And if you play the game carefully, you'll see the shapes that make the cats react like this are really inside here. And this actually finishes the argument. You just keep adding more cats, and they allow you to detect the one shape that appears infinitely many times. And like the cherry tree in the bottom of the mountain, this one shape has to actually solve the problem. So I'm not saying this is not an easy trick, right? This is a complicated trick. Some puzzles have an easy trick, and you go, but this is a complicated trick, and you go, well, give me a second. And it took people, as I said, 2,800 years to figure it out. But the good thing is, if you do these sort of things along the way, you learn a lot of useful things. And you can apply it to other problems. So now, okay, it took us only almost 3 millennia to figure out Dido's problem, but let's look at another problem. Let's assume Dido has sisters. All right, so now there's 4 queen Didos, and they have one domain in space, say this blackboard, and they want to split the blackboard somehow in a way such that you get 4 kingdoms of the same size, such that the boundary lengths combined are as short as possible. Right? Previously, I had one kingdom of a fixed area, and I want the boundary length to be as small as possible. Now I've got 4 kingdoms, or 50 kingdoms, and the sum of the areas is supposed to be as small as possible. How do you do that? It sounds infinitely more complicated. Well, let me introduce you to Queen Dido and her sisters. Bees have that problem forever. Bees want to do precisely that. They want to split things into honeycombs of the same area to put the honey in, and they want the boundary length to be as small as possible because they have to actually build it, right? I mean, they have to actually build it, which is a lot of work. If you've got a complicated boundary that is very long, it takes you a long time to build it. If it's short, you're very efficient. So bees seem to have found the perfect configuration for thousands and thousands of years. And this observation is actually 2,000 years old. It goes back to Marcus Terentius Varro, who was a Roman scientist who wrote about things he saw in the garden, on the countryside. And he says, well, you know, the honeycomb clearly has a hexagonal shape. I mean, there's 6 sides to the boundary because the bee has 6 feet. Right, so it nicely fits in. Well, no, not quite. But this was the first time this was mentioned. And again, it's a very, very complicated problem, and the solution took 2,000 years. And it was actually solved 15 years ago, so not too long ago, in 1998, 1999, around that time, by Thomas Hales, who is still alive and well. And he said that the bees are actually right. This is the perfect way to distribute things. It's a remarkable statement. It's also a very complicated argument. And there's no reason to stop there. So one example is, suppose I actually give you a square and ask you to not put it into a lot of small areas, because bees know how to do that. I ask you to put it into 4 or 5 subsets, 5 kingdoms, to minimize the area. What does it look like? This, that? We don't know. We have no idea. It's a perfect puzzle, and we don't know what to do with that puzzle. We don't know how to answer the problem. Just to say, there's a lot of open problems out there that still need to be solved. Let's talk about houses. Suppose we're like the bees, but we like to build houses. And you know, you've got 7 kids. You want every kid to have a room of the same size. Otherwise, there's trouble. Trust me, I know. And so the houses have the same, the rooms have the same size, and you want the boundary length, which is now the walls, to be as short as possible. Why? Because they're expensive to build, right? If you can build short walls and can get the job done, build short walls. The reason we don't do it, it's not very nice to live in these places. So Kelvin, Lord Kelvin, was one of the first to think about this problem, and he said this has to be the solution. This is the 3-dimensional analog of what bees are doing in the plane. And it's a very old conjecture, and we still don't know the answer, but we know one thing. And this is also nice about math. Lord Kelvin, who was a brilliant man, I mean, we named temperature after him, right? He's a very smart scientist. He was wrong. So there's at least one configuration that is better than what Lord Kelvin proposed. It was discovered by physicists in 1993. The perfect configuration is still unknown. We don't know what 3-dimensional bees would do. Okay, bees are 3-dimensional, but the houses they build are 2-dimensional, essentially. We don't know what a 3-dimensional bee would do. And another nice aspect of math is if you get pretty pictures like this, you can sometimes convince people to put them into reality. So this is the Beijing National Aquatic Center that was built for the Olympics in 2008, and it's based on that shape, that configuration. Here's another problem, and this is again a problem of the following type. We now know there is an answer, thanks to the same reasoning, thanks to the same game with the convex shape, it's the same principle, we know there is an answer, but we don't know what the answer is. So the problem says, suppose you have a worm of length 1, maybe a pet rain worm, and whenever it falls asleep, you want to cover it with a blanket. And you like your worm very much, so you want the cover to be made out, the blanket to be made out of gold, right? Sure. Gold is very expensive, so you're looking for the smallest possible blanket that will cover the worm, no matter how he falls asleep. Okay, it's an interesting problem. And you can say that a circle with radius 1 will work, because you just put the center of the circular blanket on top of one of the endpoints of the worm, and the other side has to be within a radius at most 1, distance at most 1, so it's contained fully inside the blanket. All right, but that's 3.14 areas. That's a lot of gold. If you think smart about it, a circle with radius 1/2 will also work, because you can put the center of the circle at the middle point of the worm. The middle point of the worm has the property that all other points are at most 1/2 of it away. Distance at most 1/2 from the middle point. So they're fully contained inside a circle with radius 1/2. And with a little thinking, you've reduced the area by a factor of 4, which is great if you want to save money. Now it gets tricky. Half a circle with radius 1/2 also works. And the argument is more complicated. And people actually kept thinking about this, and the best result is somewhere in here. So we don't know what the best shape is. Probably it's very pretty to look at. But we know its area is somewhere between 0.21 and 0.28. And one thing that's happening is Blaschke tells us there has to be a solution. Because you get a sequence of convex shapes, you get an infinite number of solutions. Right? You take a better and better and better and better solution. You get more and more blankets. And you've got infinitely many blankets. There's got to be 2 that look very similar. As a matter of fact, there's got to be infinitely many that look very, very similar. And they have to look similar to the real answer. It's again the cherry tree in the valley of the mountain. And this makes it, of course, more tempting, because we know there is an answer. We just don't know what it is. And it's always bugging me. OK, let's return back to nature. We started with the nature of the circle appearing everywhere in nature. And we got a beautiful mathematical problem out of it. So the last few slides are to convince you that nature is still amazing. And there's still many beautiful problems that need to be solved. And we don't know why things happen the way they happen. So this is something you get when you mix iron. There's a lot of different irons in chemistry. I'm not a chemist. I read about this on Wikipedia. But what you have is if you mix iron, you get shapes mixing in that form. And it's called the austenite and the martensite. And they mix in a very, very complicated way. You get one entirely on one side, and you get another one that's sort of mixed up in weird lines that have a certain ratio. And that can be observed for a couple of materials. And people are actually pretty close to figuring out why that is true. But it's one problem that just appears out of nowhere, and you try to understand the reason for this happening. There has to be a reason. It doesn't happen randomly. There's some structure behind it. You have to discover it. This is another nice example. It's a volcano eruption in Northern Ireland that gave rise to this constellation. There are 40,000 stones like that. So the picture only shows a couple. And if you look at the stones, most of them have 6 sides. A couple of them have 5, a couple of them have 7, some are 4, some are 8. No triangles. Most of them have 6 sides. It's not clear why that happened. So you have the volcano eruption, you've got sort of lava flowing, and it sort of crystallizes in that form. It's not clear why it would do that in that shape. People are trying to understand it, and there seems to be some connection with problems arising in analyzing images on the computer. So completely unrelated topics might have some impact on this. So here's something that I spent many years thinking about, and well, I'm still thinking about it. It's difficult. If you do this, you've got vibration in the desk. There's one big vibration wave, and that makes a lot of noise, and that's what we hear. But on top of this one big oscillation, there's one big vibration going through the desk, there are many tiny vibrations on top. And you can't hear them because they're tiny. But if you zoom in large enough, you get structures like this. And if you zoom in into atoms, you see the same structure. Atoms are really like tiny vibrations. So you get this shape. And sometimes it looks like this, and sometimes it looks like that. And to get back to a recurring theme of this talk, the problem I've been thinking about is how many of these bumps can there be? Right, you get a couple of ups, you get a couple of downs, here's bumps, here's bumps. How many bumps can there be? I think the worst case is hexagons, like the bees. If this has a B-type shape, I think this is the worst possible case that can happen. But we don't know why that is true. The computer seems to agree with us, and it seems to really be that hexagons again appear as the limiting case. But we have no idea why. We need a couple of new ideas. And the final picture, these are liquid crystals that are also being actively studied and give rise to very beautiful pictures. OK, so I want to finish with saying that there are many very nice problems in nature that need to be analyzed that give us shapes. And we would like to understand why the shape is the way it is. Why is it that shape and not another shape? And nature tends to be pretty smart at these sort of things. So nature's usually right. But we don't know why. And in the end, you do want to know why. OK, thank you very much.